Okay, let's do another example. In this particular case, I'm looking right here, and I have A, B, C, and D, 4 points of interest there. And if we notice here, I'm below a lake. And so I'm going to take that into consideration and see what that does for us. We make the same table we've been making, which is our point depth, sigma u, sigma prime, and so let's do these points one at a time. So I've got A, B, C, D. Here are the depths, 12, 15, 20, 31. I can look, my water table is up here. So here's my water table is at the ground surface. So what do I see? I don't use any of the dries. So I cross those off. And I circle both of the saturated unit weights. And what do I see here? So I'm looking at point A, and what is above point A? Well, it's 12 feet of water. That's it. So my sigma is 12 feet times 62.4 pounds per cubic foot. For point B, I've got 12 feet of water and 3 feet of saturated clay. 12 times 62.4 plus 3 times 112. For point C, I've got 12 feet of water plus 6 feet of clay plus 2 feet of gravel, all saturated. 12 feet of water, 6 feet of clay, 2 feet of gravel. For point D, I've got 12 feet of water, 6 feet of clay, and 13 feet of saturated gravel. 12 feet of water, 6 feet of clay, 13 feet of saturated gravel. My pore pressure, well, I put a piezometer for A. Well, where does it go? 12 feet. For B, goes 15 feet. For C, up to the water level, 20 feet. For D, 31 feet. And then sigma prime is equal to sigma minus u. I simply sigma minus u equals sigma prime. Okay, very straightforward. Okay, I want to talk about an issue here that I want to get straight here, and that is what happens if the water table level is in clay or silt. Now, why is this an issue? This is an issue because, if you remember, clay and silt are fine-grained soils, and one of the things that distinguishes it from coarse-grained soils is that fine-grained soils hold the water. It's not once they're wet, they don't want to let go of their water. You've probably experienced it in the lab, where the only way to get the water out is to put it in an oven or let it dry out. Okay, well, once it's in the ground, it doesn't dry out very easily. It can dry out, but for the purposes of this class, we are going to ignore the very, very top layer. If you have clay, so in other words, if I have clay at the ground surface and it's in a dry climate or a dry period, what's going to happen is that the top of the clay will dry out. But I'm going to ignore that effect for this particular class. And what I'm going to say is that when the clay gets saturated, I'm just going to assume that it stays saturated and it's going to be like that. So, and then what I'm going to tell you is that the way that we're going to consider this is we're going to consider that clay is saturated and silt is saturated, and we're not going to look at dry clay or dry silt. And I'll explain why. I'm going to give the answer on how to do this first, and then I'm going to explain why it's that way next. So let's do the answer first. So let's look at this. I've got point A, point B, point C, point D. And my top layer is clay, and I have my water table in the clay. And I have then gravel and sand below that. Now, the impact of this, here's my water table level, and you're going, wait a minute, if the clay is completely saturated, why is that the water table level? Why isn't the water table level at the surface? And I will explain that next. But for the time being, I want you to accept that there's my water table level, but all of this clay is saturated, completely saturated. And what is the impact of that? So so in other words, all of this soil now is going to be considered saturated. Why? Because the clay, even above the water table, is saturated, and then I have my water table level, which means that all of the soil down below the water table is saturated. So everything's saturated. So I'm going to cross off my dries because I'm not going to use them. I'm going to circle all my saturateds, and I'm only going to use saturated unit weights. Okay, so let's start with point A. Well, it's 2 meters down, so it's 2 times 18. Point B, everything above point B is saturated. It's at 8, so it's 8 times 18. Point C, I've got 11 feet of saturated clay and 10 feet of saturated gravel. So I got 11 times 18 plus 10 times 20. Point D, I've got 11 feet of saturated clay, 21 feet of saturated gravel, meters, and 14 meters of saturated sand. So 11 times 18, 21 times 20, 14 times 24. I get 954. So yeah, it's important that you remember whether you're working in English or metric. Why? Because when you come to pore pressure, you have to make sure you use either 9.8 or 62.4. So pay attention to whether you're using metric or English units. Let's work the U from the bottom up. I'm going to do point D first. So I put my piezometer at D, and what do I get? It goes to the water table, and that works out to be 40 times 9.8. I put my piezometer at C, goes to there, and that gives me 15 times 9.8. Point B, very short, it gives me 2 times 9.8. Okay, now here's the hard one, is A, okay? So A, since it doesn't make much sense to put a piezometer here, but I'll show you how we deal with it. But point A is 4 meters above the water table. So like I say, I'm going to give you the answer, and then I will tell you why in a second. So the answer is it's above the water table, so it's negative, and it's 4 meters above the water table, so it's -4. -4 times 9.8, and I get a negative pore pressure. So my pore pressure is -39.2. My sigma prime is the usual, sigma minus u, and when I do that, what am I going to get? Well, I'm going to get, for the first one, is 36 minus a negative 39.2. So it's 36 minus negative 39.2. I get 75.2. So I have to be true to my numbers when I do this and use that negative sign. For the others, they're the same as 144 minus 19.6 and 398 minus 147 and 954 minus 392, 562. Okay, so the question is let me describe why is that a negative 4 times 9.8. Okay, why is there negative pore pressure? That's the question. You need to recall from your chemistry class, if you remember, about capillaries and a thin tube and what happens in a very thin hollow tube. In other words, something like the size of a human hair, hollowed out, very tiny thin tube. If I put that into, let's just say I have a container of water here, and I put a very thin tube into it, well, that's hollow, well, what's going to happen? Due to the principle of capillarity, water goes up the capillary. And if I look at what I want to do is I want to take a free body diagram now of that water that's in that capillary tube, and I've made it bigger. So there is my free body diagram of the water in that capillary tube. And so here's my water. And what's acting on that water? Well, if you remember your chemistry, what do we have? We have a meniscus in that capillary tube. And why do we have a meniscus? Because we have surface tension. And that means that, what is it? Surface tension. So I'm going to put some tensile forces here acting in that direction because that's the way they act. That is my surface tension of the water. Now, it's approximately 0.073 newtons per meter is that surface tension, and it takes place at an angle of alpha. And so there's some forces on my free body diagram. What else do I have? I've got my water, which gives me the weight of the water. I have the weight of the water. And then at the base here, I have pressure acting upward. Now, the question is, what is that pressure? Let's look on the bigger picture up here. So let's look up here and try to reason out that pressure. Well, ignoring atmospheric, so in other words, I'm going to say the pressure here is 0. The pressure there is 0. It's atmospheric pressure, but we're just going to cancel that out for the time being. But what do I know? This is in equilibrium. In other words, it stopped moving. If I want to compare the pressure here to the pressure, right there at the bottom of our blue water, put it this way: if the pressure here is greater than the pressure at the bottom of that blue water, then what's going to happen? Then there will be flow like that. But since it's not moving, it's in equilibrium. So if it's not moving, then what do I know? Then I know that the pressure here is the same as the pressure right there. And since the pressure here is 0, we just decided it, then the pressure here is 0. It's the same. So right there, I've got 0 pressure. So I can, basically just ignore it, 0. So what happens is that this tension, the way to look at that, that's going up. This way the water is going down. And let me just note that for water, the alpha is approximately 90 degrees. So I didn't draw it quite as well as I could have. But it's 90 degrees. So what do I see? I see that this surface tension is going to be equal to the weight of the water. And what happens is that the weight of that water depends on the diameter here. and what we find is, if I did the calculation, which I'm not going to do, is that we can calculate this HC, in other words, that for the various Ds, for the various diameters. And let me make one other comment here. Notice the units here on the tension is 0.073 newtons per meter. Well, what does that mean, newtons per meter? Remember that this goes around the circumference of our little hollow hair. So that's where the meters come in. It's the circumference. So put it this way, we could do the geometry and we could figure all this out, and we would be able to get an HC for each D. As D gets smaller, notice what happens. When D is small, HC is very big. Or sorry, I circled the wrong ones here. When D is small, HC is very big. When D is, this is big, 0.01, HC is small, 30 times 10 to the negative 2. So the smaller that the D is, the bigger the HC. Now, what does this D have to do with our soil type? Well, the D is what? Is the diameter of the hollow tube, or the size of our soil void. And what do I know about clay and silt? Well, the voids in clay and silt are very small. So I'm going to be down, silt and clay pore size is going to be down in here. So I'm going to get an HC of 3,300 meters. So what that means is that if this is my saturated soil down here, and there's my water table, notice the water goes above the water table. So up here it can be saturated, so that's also saturated soil, but my water table is still down below here. So that is the phenomenon we were looking at in the previous problem that maybe didn't make much sense at first, but now it should make sense when you think about this effect of the capillaries. And let me make one other point here, and that is that if I'm looking at the pore pressure up here, what do I know? It's tension. And the smaller, and it ends up that if you look at it, this entire water column is in tension because it's 0 down here, but it's tension there, and it's even more tension there. So as we go up this water column, we get more and more tension. So that is the reason that let's go back to this page here, that is the reason that we have the -4. Why? Because we're 4 meters above the water table here. And so as we get closer and closer to the water table, it'll be that won't be -4, it'll be -2, -3, -1, something like that. So the farther we are away from the water table, the more tension that we have. Okay, so you need to be aware of that. You need to be able to recognize that if I have my water table in a clay or a silt, and I'm considering a point above that clay or silt, I want you to consider the pore pressure as being negative. And I just showed you how to calculate it. Okay, here's an example of this. So I have a clay. There's my water table right there at 5 meters. Now, what I want you to do is say, okay, this is all going to be saturated here. So when I do my problem, I cross off my gamma D because nothing is dry, and I just use the saturated. So I'm looking at so I have A, B, C, D, E. I have, so A, B, C, D, E right there. These are the depths of each of those points. Notice that my water table is at 5. So, but let's look at what I have. Well, at 2 feet, I have 2 times 20, meters. 4 meters, 4 times 20, 5 meters, 5 times 20, 6 meters, 6 times 20, 7 meters, 7 times 20. And so I get all my sigmas. The only hard part in this problem is the U. Well, let's do it from the bottom up. So point E, I'm 2 meters below, so 2 times 9.8. Put in my piezometer at D, I'm 1 meter below. 1 times 9.8. Point C is at 0, right at the water table. Now point B is what? 1 meter above the water table, so it's -1 times 9.8. Point A is 3 meters above the water table. So it's -3 times 9.8. And then again, we use our basic formula that sigma prime is equal to sigma minus U. And we get these numbers here from all those columns. Okay, so I want you to use that in this class, in that clays and silts, they're going to be saturated above the water table. Okay, so I want to talk about horizontal stress. And in other words, to this point, we've been talking about vertical stresses. Oh, that's in the vertical direction. Well, what's the horizontal stress? First thing I'm going to do is I'm going to define something. I'm going to define a K as being sigma H prime over sigma V prime. Sigma H prime being horizontal effective stress. Sigma V prime is vertical effective stress. And you have to remember, this is not sigma H over sigma V, it's sigma H prime over sigma V prime. So we have to remember the prime here. It ends up to be a very important part of this. And I want you to memorize this expression. And then we're going to have 3 different subscripts for the K. We're going to have a Ka, a K0, and a Kp. And I'm going to note that Kp is the biggest, Ka is the smallest, and K0 is in between. And I will describe what the meaning of these is. K0 is called the at-rest earth pressure coefficient. What's the concept of this? Suppose I have a bucket of water. So here's my bucket, and it's just water in here. Okay, so you've all experienced this one. Now, I'm going to take that and I'm going to apply 100 pounds per square foot at the surface of my water. And now I'm going to ask the question, is that when I apply this at the surface, my question is, what does the wall feel? How much of that 100 psf gets translated to the wall? That's my question for you. And the answer is that all of it is so what increase in wall stress, horizontal, do we get due to the 100 psf? The answer is 100 psf, because that is the way water works, right? You push it one direction, goes the other direction. It doesn't matter that one's vertical, the other's horizontal. You're going to get 100 psf. So that goes back to your fluid statics. I'm not going to review that. I think you can all have a conceptual feel that that is the case. But now let's take a bucket of dry sand and do the same thing. So I have my bucket of dry sand here, and now I'm going to apply 100 psf downward. And the question is, what does the wall feel now? It's not water, it's sand. So what increase in wall stress do I get due to the 100 psf? Well, the answer is less than 100 psf. For sands, we're going to get a K0, say approximately 0.4. This is a rough estimate, don't use this all the time. But it's not a bad number, which means that the answer would be 40 psf for that particular sand. Each sand will have a different number for that. Each different type of sand, for instance. So I apply 100 at the top, but the walls only feel 40. And that means that my K0 is 0.4. You can measure this in the lab. So that is essentially the meaning of the word K0, the at-rest earth pressure coefficient. For clay, a better estimate of the K0 is about 0.6. So now I want to say something about, well, I want to emphasize this. K0 is called at rest, meaning there's no wall movement. In other words, when I apply this 100 down that way, these walls are fixed. They don't move. In other words, I'm going to assume that this is completely rigid, that bucket, and that this wall, that there's no tendency for this bucket to get, a little bit bigger here, to make a, create a bigger bucket. So we have no wall movement, perfectly rigid walls. That is the meaning of the K0. That is the meaning, no wall movement. Okay. I want to introduce some wall movement here, and the active earth pressure coefficient and the passive earth pressure coefficient. I'll sort of use bookends, something that you've had experience with. There's a bookend yourself. So the bookend is a little bit like a soil retaining wall. And what I'm going to say, I'm going to finish this in another lecture, but what I want you to just think about is that you've all done this. You've all moved into a new apartment or something like that, and you needed to put your books up in the bookshelf, and you stack your books nicely. You take your bookend and you put it up there. And I want you to think about what happens after you put your bookend up there and what you normally do. And I will finish this up in the next lecture.